I hope everyone is doing good and great. I am Mahesh, your physics teacher, and you're watching me on SMR Online Physics. In the last class, I discussed about microscopes. So naturally, today I'm going to discuss about, yes, you guessed it right, telescopes. How exactly telescopes work out? How do they magnify a far away object and really brings it at closer, and we are relaxed. Our eyesight is very relaxed. So there are two possible adjustments in which I can see the object which is very, very far away, closer to me, that's magnified. So how do that exactly work out? Very simple. If you haven't watched my previous video on microscope, please do watch it. Then you'll get it much more easier to understand how a telescopes actually work out. So here we go in understanding telescopes. Come on. So telescopes can be of two kinds. It can be refracting telescope or reflecting telescope. So it can be refracting telescope or it can be reflecting telescope. So I think most of you can even guess it. In refracting telescope, it will be a combination of lenses. And in case of reflecting telescope, it will be a combination of lens as well as mirrors, right? So today in my class, I will be discussing about the refracting telescopes. Okay? So let's get started with the first one, astronomical telescopes. Right. How exactly an astronomical telescope works out? Keep it simple. Please focus on the diagrammatic representation in case of astronomical telescope. Okay, here also you require two converging lenses. Point one. One is called the objective, the one which is closer to the object. The other one is called the eyepiece, the one which is closer to my eyes, through which I will exactly see it. So both these lenses are placed into cylindrical tubes whose adjustment can be done. The length of the distance between the two lenses can be adjusted so that the cylinders can be moved in and out. So in this case, the objective, mind it will have slightly longer aperture or longer focal length in comparison to the microscope's objective. All right? So let me draw a neat and clear diagram of the objective and the entire astronomical telescope. So let's say this is our objective. Let us represent it by O. Great. And let us say it has the focal length of f0, which always reminds me about the focal length of the objective eyepiece. So then we get our principal axis as a reference. Let us say this is the principal axis. So here you're trying to see something which is very, very far away. So let's draw an object which is actually very far. A distant object. Something like this. Let us call it as A, the head, and the B, the foot. So light rays actually travel from this enormous distance and happen to pass through the objective of the lens. So as this passes through, the lens makes it to refract. Then another ray of light, let us show it through the principal axis, through the optical center, gone, undeviated. Another ray of light, let us show it, it's like a panel beam of light coming from the very distant object, passing through my objective eye lens. Then you find that it refracts it, and that's it. I hope my diagram is crystal clear so far. So here you find that from the knowledge of how do lenses actually behave in formation of image, the light rays coming from this far away object, like object at infinity, the image is always going to form at the focus, right? So this is what the image is. As you can easily see that it's a tinier image, but inverted at the same time. So let us say this is my A1, this is my B1. Now what we do is that we place another lens. We place another lens which I call as the eyepiece. So the eyepiece should be kept a bit in such a way whose focal length is relatively smaller than the focal length of the objective. It's kept in such a way that this image formed by the objective falls within its focus. Is within its focal length. I mean to say, so let us say this is your focus of the eyepiece. So then this distance will be called as the focal length of my eyepiece. So when the object is placed between the optical center and the focus, then you know what's going to happen. The image is going to form at infinity, very far away. Not exactly infinity, I mean to say it will form on the same side where the object is, and it will be a magnified image. So what exactly happens is, this light rays, you can trace them, it comes through, it bends, it comes through, let me just close it out here, then it again bends, great, this light ray comes in here and bends. So now this eyepiece has done that, so let me call this as E for eyepiece, and let it have a focal length of Fe. Great. So these light rays finally enter into the observer's eyes. So this is my eye. Great. So what we find is that when I produce this light rays straight through, the image is formed somewhere very far. And where it will form, that will depend upon the adjustment of the two lenses. So yes, somewhere here. So you can even show that. Absolutely. It isn't easy to draw these straight lines without any scale, and you find that, yeah, pretty good. I agree for that. I hope you too. So this is where the final image of this object is formed. So this is inverted but pretty much magnified. So this is the final image formed. So let us name this as A2, and this is the B2. So my dear, I hope you have understood this entire process of drawing the ray diagram for an astronomical telescope. The object is AB, light rays pass through my objective, image is formed, diminished but inverted, and this object, this image of this object behaves like an object for my eyepiece. Simple. So this eyepiece is going to allow this light rays to pass through it, refract it, and hence you get the magnified image. That's how an astronomical telescope functions. Okay, great. So let's see the mathematical implications of it. Very simple. From here till this point, this distance has to be called as the focal length of my objective. This is F0. Similarly, if you want to see this, this has to be called as Fe, the focal length of my eyepiece. Then you can also see that this has to be called as the object distance for my eyepiece, and hence this has to be called as the image distance for the eyepiece. That's your final image distance. Everything is clear, I suppose? Right. Am I clear, dear students? Right. So let's mark it up. This is my PO. Let's say this is my PE, maintaining the same subscripts. Everything good and great. Let's do the simple mathematics. If you have observed and if you have followed my previous classes, it's easy to see that this device has actually improved the angular magnification. Otherwise, our eyes would have been good enough. So they'll act like an aid to our eyes. So what is the angular magnification created by this device? I always try to notify it as m of theta, angular magnification. So angular magnification, my dear, is always represented by the angle subtended to the eye by the image, by the angle subtended by the object to an eye. So whereas the betas and alphas, absolutely this was the object. So this has to be my alpha, this has to be the alpha, vertically opposite angles. So this is my final image. So these are the light rays reaching to my eye. So this is your beta. That's it. Come on. You can do it by yourself. Nothing to worry about it. So what's the beta? What's the ratio of beta? You know that. So this is perpendicular. This is the base. So you can happily write it like A1B1. A1B1 divided by, you can say B1PE, the optical center. Is that visible to you? Great. Okay. And then we again see for alpha. What is alpha here? This is the alpha. This is the triangle created. So this is your perpendicular A1B1 divided by the base, that is P0 B1, or we'll say the same way B1 P0 or PO. Right? So you can easily see that how easy it can be. M theta is equals to A1 by B1 P, and you get it clear, na? B1 PO by B1 PE. That's it. Put it in with your proper sign convention. Everyone should know the sign convention. Okay, we are about to wind up ray optics with this class. So B1 P0, what is that? This is for this lens, so this has to be its image distance, as well as that is also the focal length for the lens. So I will call it as positive F0. Great. And what is B1 PE? This is the object distance for my eyepiece. So it's on the left hand side. So minus UE. Great. Simple. That's it. I hope you are very clear till now. This is your angular magnification, what you can find. So now there can be two possible adjustments of an eye with respect to the telescope. If you want to form the image at your own near point, that is equal to 25 centimeters on an average, then the conditions will be slightly different. Or if you want it to be, the image should form at infinity and your eyes need to be very relaxed, then also we can do it and find out how the angular magnification can slightly vary. Great. I hope I'm clear till here. Come on. Okay. So now we shall extend the formula for angular magnification. So let me write down what we got so far. We got m theta, the angular magnification, is minus f0 by UE. I think it's not blurred away. Yeah, you know that. So we can continue with that way, and we can see for the conditions of this eyepiece. For the eyepiece, let us write down the conditions, right? For the eyepiece, I find that the object distance is this, to the left hand side. So it should be mentioned as minus UE. Great. And for this, the image distance again forms to the left hand side. So it remains as minus VE, and the focal length is always positive sign for a convex lens, right? So therefore we apply this lens formula, the thin lens formula, with the proper signs, and we find we can do it. This is minus this. This is minus UE is equal to 1 by FE. And from here my actual goal is to get the value of 1 by UE, right? So 1 by UE is equals to 1 by FE plus 1 by BE. I'm sure you're getting it. Yeah, I went too low. We couldn't see that what I wrote over there. So I've taken, my board has taken all the space for the diagram, right? So you find 1 by UE can be written as 1 by FE plus 1 by BE. That's it. Now this value of 1 by UE, I can put it in the formula what we have obtained so far for angular magnification. Right? So the next formula what I found is 1 by UE is equals to 1 by FE plus 1 by VE. This I'm going to put in there, right? Am I clear? Come on. It's very, very easy, very, very easy. Students tend to feel it tougher sometimes because of the diagram probably, but I think I have made it easy for you. Therefore, and do not forget to mention your comments in the comment section below. Alright? Feel free, come on. So you'll have minus F naught by 1 by UE, isn't it? 1 by UE is all equal to this. 1 by FE plus 1 by VE. Just we'll do some arrangements like minus F naught by minus FE. That is the fractional ratio of the focal length of the objective to the focal length of the eyepiece. So hence you end up getting 1 plus FE by VE. That's it. This is your final expression for the angular magnification achieved by an astronomical telescope. I'm sure I'm clear till here, right? Now here onwards the telescope can have two possible adjustments. The two possible adjustments, as I said already, it can be for viewing the image at my own near point, or if the image is formed at infinity. Alright? So let's get rid of this equation. Let me use some space from here. This is my VE. I maintain that. I do not want to get rid of this diagram, that's why. So I note down the equation. M theta, that is angular magnification, is minus F naught by FE into 1 plus FE by U. Sorry, that is VE. Am I good there? Correct. That's it. Now let's do the two possible adjustments. The first possible adjustment for the astronomical telescope is if image is formed at the near point. Means if the image distance becomes equal to D. Alright? This is this. If this image distance is formed at your own near point, which we denote as capital D, which is equal to 25 centimeters for an adult eye. So VE should be replaced by capital D. Therefore, the expression for angular magnification will look like minus F naught by FE into 1 plus FE by capital D. That's it. Simple. I get your point here, right? Great. So now what is the other condition left over, my dear? The other condition is if this image forms at infinity. When will this image form at infinity? When the object distance, if this object for this lens forms exactly at the focus of this eyepiece, then the image will form at infinity. So I can rub it off from here and we can note it down. Number 2, feel it easy. Number 2, if the image is formed at infinity, if it is formed at infinity, then we can write the object distance should be equal to, what is that? It should be equal to the focal length. Definitely it should be equal to the focal length, and you can easily see from this equation UE should be equal to FE. Therefore the angular magnification achieved will be is equal to minus F naught by FE. That's it. That's it what you have for astronomical telescope. Alright? I hope I'm very clear in this video about how an astronomical telescope achieves the magnification. So once you have understood this, the terrestrial telescope can be easily understood, because in terrestrial telescope everything remains exactly the same except for an erecting lens, which is a converging lens which is placed in between these two, will help you to see the image erect and magnified. Here what you find is that the image is magnified, but it is inverted. That is only only the difference between these two telescopes. Hope I am clear, not for the last moment where I stammered out. Okay, thank you very much for viewing, and thank you very much for coming back to SMR Online Physics. If you like my classes, please do like, share and subscribe my channel if you're new to it. Alright, see you again with something very fresh from physics classes. Thank you.